I'm looking for 3 of you. Okay. Danish is here. Danish not here. Okay. Arif here. Arif not here. Okay. Kayan here. Why Kayan? Okay. It's just like anyone close friend with the Kayan? Do you know what happened to Kayan? No idea. Okay. Is she in the WhatsApp group? Yeah, the admin, the group admin. Can you please check? Is she in the WhatsApp group? Maybe Celine. Do you know her well? Celine here, not here. Celine. Okay, so if you get to know well, can you check whether she's in the WhatsApp group? I'm not sure because the photo is not there. Okay. Yeah. So if you close with her, can you ask her to join the class? I don't know what happened to her. Okay. So let's restart today's lesson. Okay, class. So can you see the slide, right? Can you see the slide, Sorry.
Yeah.
Okay, thanks. Okay. So let's continue. So what you learned so far in magnetic field, So you learn F equals to BIL. First, you learn about the magnetic field pattern. Then you learn about F equals to BIL, current carrying conductor, the force you need to calculate by using BIL sine theta. Then towards the end, we learn about how to calculate the force to a moving charge. So we found it's BQV. BQV is actually formed from BIL. So yes, BQV sine theta. Theta is the angle between the direction of the charge flow and the magnetic field. Direction of the charge flow and the magnetic field. So in this case, I think the theta should be here. Let me show you. So the theta should be here. This is the theta. If the V is here, this is your theta. Okay, the angle between the velocity of the charge and the magnetic field strength is your theta. Okay. Okay. So BQV sine theta. Okay, now one example of that: a proton and electron enters a magnetic flux density of 0.04 Tesla perpendicularly. Both particles travels at the speed of 2 × 10⁶. Okay, charge each of them is the same. Draw on the diagram the direction of the magnetic force acting on the proton and electron. Okay, draw on the diagram the direction of the magnetic force acting on the proton and the electron. Okay, proton, tell me, is it which direction, up or down? A little diagonal. So use your Fleming left-hand rule. Check. Your index finger is your magnetic field strength into the page. Cross means into the page. Current is to the right, towards the right. So the force should be upwards. The force must be this way. Correct. Correct, right? FBI. B is into the page. Current is to the right. Because positive charge to the right means current is to the right. So force upwards. Okay, negative. Which direction? Get me? Which direction is the force? FBI. Magnetic field is into the page. FBI. I is to the current is to the right or left? The electron is moving to the right. The negative charge is moving to the right. So current should be to the left. the electron move to the left, and current should be to the right. So the Fleming left-hand rule is pointing the current. So put the current correctly to the right, FBI. So the force still upwards. Force still upwards. Yeah, good, correct. Okay, draw on the diagram the direction of the magnetic force acting on the proton and electron. What is the magnitude of the force which the magnetic field exerts on the proton and electron? So how much is the force? So use B QB to calculate it. So both of them have the same speed, both of them have the same charge, both of them have the same magnetic field strength. Therefore, the magnitude of the force is going to be the same for the proton and electron. Okay. So yes, so this should be in your mind, sine 90, because V assumes perpendicular. The V and the magnetic field into the page is looks like perpendicular, so sine 90. If angle is not provided, you take it as 90. Okay, so this is the direction of the force. Okay. Okay, next. Okay, now something important. So look at the first diagram here. The V is to the right, force is down, magnetic field is out of the page. Dot means out of the page. The force will be down. Okay. So here you have to be noted that the force and the velocity is always 90 degrees perpendicular. 90 degrees. If a force applied perpendicular to the velocity, what type of path the charged particle will take? The force F acting on the charge entering the magnetic field is always perpendicular. It's always perpendicular to the direction of the speed. Okay. Can you predict the trajectory of the charge of the magnetic field? How the particle going to move? Circular. So you're going to move a circular path. Okay, it's a circular path. Okay. If the velocity is this way, force is this way, so the velocity will change direction. If the velocity here, the force will be here. It always 90 degrees. So if the force is always 90 degrees, what happened? It make a circular path. It will make a circular path. Okay. What is the condition to make a circular path? The force is always perpendicular to the direction of motion. So that happens here under magnetic field. So charged particle will make a circular path. So the magnetic force is acting as the centripetal force. So Q, positive charge, moving like this. So it's make a circular path. Okay. So now because it makes a circular path, now you have to recall back all your circular knowledge. Okay, all the equations you need to recall back. Because the question now, magnetic field, they're going to include circular path. They're going to ask about what is the radius the charge will make and enter a field with a certain speed, with a certain charge. Okay, they're going to ask what is the radius it make. So you have to use your circular motion knowledge. So positive will make a circular path, this path, correct? Positive magnetic field is into the page, charge particle moving up, use Fleming left-hand rule, force must be towards the left, so you make a circular path to the left. Yeah, and the same thing, all going to make a circular path. So apply Fleming left-hand rule to determine the direction of the circular motion. If the force is to the right, it's going to make a circular path to the right. If the force is to the left, it makes a circular path to the left. So take note, the radius of the circular motion is dependent on the speed of the charged particle. Yes, the radius you're going to make is depend what speed it's traveling. Well, let me interpret that in the next slide. So whatever it is, charged particle enters in magnetic field experience circular path. Okay, class. What type of path experienced by the charged particle in electric field? In electric field, the charged particle will experience a parabolic path. Gravity also parabolic path. Magnetic field is circular path. Why in electric field it makes a parabolic path? Because the force acting in a fixed direction. If the force acting on a fixed direction, it makes a parabolic path. If the force is always perpendicular to the direction of motion, it makes a circular path. Okay, now come to the important slide. So I don't want to read the first one. The BQV equals to mb squared over r. The magnetic force is equals to the centripetal force of the particle. So recall back the centripetal force mv squared over r, or can be what? Another one, mr omega squared, right? So two formulas. So depend which is more useful. I have to check. If they're asking for frequency, then you need to know the omega. Then you use mr omega squared. But very common we use mv squared over r here. So BQV equals to mv squared over r. So make the V as a subject, r as a subject. Sorry, you get the radius formula. This is the radius formula. Okay. So a lot to interpret from this formula. So more massive the particle, the radius get greater. Proton, electron, proton have a high chance to make a big radius, more massive. More higher velocity enters the magnetic field, more chances to make a big radius. And of course, if the B is stronger, the radius becomes smaller. If star charge is stronger, the radius becomes smaller. So this is a very important formula you have to analyze. Okay. So mass velocity rises, radius, big radius. So proton and electron, which is going to make a high chance to make a big radius, is proton. Okay. But electron can do a big radius by increasing its velocity. Increasing the velocity or decrease the magnetic field strength. It can increase the radius. Okay, so next, the R is the radius of the curvature of the M, the mass of the charge. Okay, if the T is the time taken to complete one revolution of circular motion, so V equals to R omega. So 2 pi, omega is 2 pi over T. So you substitute the V inside this formula, you get the period formula. This is not that important. Okay, good to know, but you have to remember the first one. But you can get all the equation just remembering the first line. BQV is mv squared over r. Then you can develop the others. Okay. So this is radius made by charged particle. Okay. Centripetal force is contributed by the magnetic force. Okay. So your turn. 1 minute. Fc equals to Fb. Anything charged particle enters the magnetic field, Fc is equals to Fb. Okay, so now try to give a try for this question. Okay. So an electron, so electron, this much of charge, this much of mass, moves in a clockwise circular motion. So it moves in a clockwise circular motion. It moves in a clockwise circular motion, electron. Perpendicular to the uniform magnetic field of the flux density of this much. Okay. The magnetic force of 5 times 10 power negative 14 Newton due to the magnetic field is exerted on the electron. Okay. So A, draw the circular path of the electron and indicate the direction of the magnetic field. Okay, let's say we use this pattern. The magnetic field is into the page or out of the page. You put a cross or you put a dot. Check for me. Let's say we put we take this location. We take this location. Okay, we take this location. Okay, use your Fleming left-hand rule. Check where's the magnetic field must directed, into the page or out of the page?
Into
the page. So is it cross? Okay, let me see. The force is to the right or left? The force is to the left, right? Because it makes a circular path in a clockwise direction. Clockwise, yes, clockwise. So force is to the left. The current is up or down. Because it's a negative charge, so current always travel opposite to the negative charge. So current is up. You use your Fleming rule. FBI, F is to the right. Your index finger, your thumb is to the right. F I is your middle finger must be upwards, so the magnetic field is into the pitch. So it's a cross. So draw a cross, it's a cross. So this is the diagram should look like for A. So I believe all of you got a cross. All of you got the imagination. It's going clockwise. All of you should know the force is towards the left because center of the circle is the force. And the current must be in opposite direction to the electron because electron negatively charged, current should be opposite direction. Therefore, use Fleming left hand rule, you've got B into the pitch. Okay, so you have to be very good in Fleming left hand rule, how to position it. Okay. Now do the B. Calculate the speed of the electron. Calculate the speed of the electron. Yeah, how are you going to calculate the speed of the electron? So the original idea is what? Fc equals to Fp could help you to find the answer. So mv squared over r should be equivalent to bqv. Bqv. So you're looking for what? Circular path of the electron. Indicate the direction of the magnetic field. We done. Calculate the speed of the electron. So we want looking for the v. What is v? V. So velocity here and here can cancel. So it's actually bqv, bqr over m. Yeah, bqr over m. So do you know B? Magnetic field, we know. Yeah, all the magnetic field is 8.2 10 to the power negative 2 Tesla. Charge, we know charge of electron 1.6 10 to the power negative 19. Velocity, do you know the speed it's traveling? Oh, we don't know the speed it's traveling. We are looking for the speed. Do you know the radius it makes? Oh, sorry.
Can you use the magnetic force to equal the magnetic?
F equals to, because F is given. Yeah, F is given, so BQV. Yeah, correct. This is easy. So BQV. So find the V. Force is given. Yeah. So force, 5 times 10 to the power negative 14. P, 8.2 times 10 to the power negative 2. Charge, Yes. So you can find the speed. Okay, so what must come to your mind is F equals to BQV to calculate your answer. Okay, so once you know the speed, now the part C, they ask you to calculate the radius. So radius now you do mv squared over r equals to the force. Yeah, no need to put BQV. Sorry, this cancel. So you can put mv squared over r equals to the force, the magnetic force. You know the m, you know the v, you can find the r. Okay, radius. Okay, understand the flow. What formula to be used, what need to be applied. Okay. So these are the answers you should get. The force equals to BQV, you find the velocity, so 3.8 times 10 to the power 6. So yes, BQV, you know already. You can put the BQV, the force, then you can find the radius. Okay.
Yeah.
So let's move on. Okay. So more questions. This is in a circular path. Tesla proton enters a magnetic field. I think I can skip this because the same way. Okay. Draw the circular path and calculate the magnetic field. Okay. So deflection of charge in a uniform electric field. Okay. So now you see magnetic field makes a circular path. BQV equals to mv squared over r. Electric field, recall back your electric field knowledge. A charged particle enter electric field makes a parabolic path. Recall back, these all are the one you learned before. The vertical force is what? QE. This is QE, charge times the electric field strength. Q we put small e. and then you can find the vertical acceleration EV over MD. F is MA. E is electric field sense, V over D. V is what? Potential difference. D is the plate separation. You can find the vertical acceleration. Okay. So why suddenly electric field comes in? This topic is about magnetic field, but why we talk about electric field now? Because the electric field and magnetic field are combined together, used together in mass spectrometer. Okay, that's why we need to bring in electric field. And in exam, another main one they're going to ask is the differences between magnetic field and electric field. Okay, so these are the some differences between magnetic field and electric field. You have to know at least two. So in magnetic field, force exerted on a moving charge particle. Yes, force only exerted on moving charge particle. In electric field, force exerted on both stationary or moving. You will experience force in electric field. Then two, the force is perpendicular to the both field and direction of the motion. Fleming left-hand rule to be used to find the direction. The force is always perpendicular to the field line. Electric field, force is same direction with the field line. In the direction of the field line. It is from electrostatic law. Like charge repel, unlike charges attract. Whatever it is, the force is always same direction with the parallel to the field line. Okay. 3. The force is dependent to the speed of direction of the motion. This is important. The force experienced by the charged particle in the magnetic field is dependent to the speed, how fast it moves. It moves more faster, the magnetic force is going to be greater. Why? Because the charged particle is going to cut the field line more greater rate, so exert more force. But in electric field, the force is not dependent to the speed. You move fast or you move slow, you get the same speed now, like gravity, gravitational force. Your weight, is it affected by your speed? Do you move fast, your weight increases? No. So same thing like electric field. Electric field, the speed does not affect the force due to electric field. Okay, and finally, another important differences. A charged particle in magnetic field tend to make a circular motion. In electric field, the particle makes a parabolic path. You must know the reason for it. Why in a circular motion? Because why? The force and the direction of motion always perpendicular. That's why it makes a circular motion. And why parabolic path? Because the force is always act on a fixed direction. Therefore, it makes a parabolic path. The reason you have to know. Okay, so magnetic field and electric field differences. Okay, so this question is about electron and perpendicular. Oh, this is magnetic field and electric field together. Okay, let's give a try. One question. So beam of electron moving a velocity of this enters a uniform electric field of this magnitude perpendicularly. Oh, that means like a parallel plate. The charged particle move horizontally. The field, the electric field, this electric field. Electric field was downwards, let's say. So the charged particle enters perpendicularly. It enters perpendicularly. Okay. To keep the electron beam undeflected. This is something new for you. To keep the electron beam undeflected, a uniform magnetic field B is applied perpendicular to the electric field. Can we do that? Okay. I need to go back to the whiteboard to explain this. Hold on, just to temporarily go to the whiteboard. Okay. See here, it's a parallel plate. This is positively charged, this is negatively charged. Let's say electron going into the plate. Okay, so the electron going to experience electric force. Which direction? Upwards. Electric force going to act upwards. Okay, so the electron should make a parabolic path upwards. But they said, according to the question just now, they apply a magnetic field in this region, so the electron moves straight line. That means the magnetic force should act which direction? Magnetic force. Magnetic force should direct it
Downwards.
Downwards.
for the magnetic force to act downwards. The magnetic field must, which direction the magnetic field must be acted? Into the page, out of the page, upwards, downwards. The electron is moving to the right. You want the magnetic force downwards. Which direction the magnetic field must be acted? Into the page?
Into the page.
Into the page.
So it's a cross. Is it a cross? Okay, use of Fleming left-hand rule. Current is to the left. So force is down. F is down. Thumb is down. Current is to the left. The page, out of the page. F B I. Thumb is downwards. I is to the left. Yeah, it should be into the page. So you must apply a magnetic field into the page. So therefore, there will be a magnetic force acting down. So the electron could move straight line. Okay. So conclusion is the Fe must be same as Fb. That's the conclusion here. Okay. All your calculation going to be based on this foundation. Fe equals to Fb to make a straight line. Okay. Fe is what formula? Q. E is your Fe. Fb is of course BQV. But E is what? V over D. BQV. So this is what the relation going to be. Don't confuse with this V and this V. This is your potential difference between the plate. This is your velocity. Okay. Go back to the question. Okay. Get me the answer for the part A. To keep the electron beam undeflected, if uniform magnetic field is applied perpendicular to the electric field, calculate the magnitude of the magnetic flux density B must be applied. Hope you get the answer bottom, 0.0402 Tesla. So you must start working with what? Fb equals to Fe. The electric force must be equal to the magnetic force. So you find B, we're looking for B, so BQV equals to QE. QE, charge cancels. So your B is actually E over V. E over V, yeah. So the electric field strength divided by the velocity gives you the answer. So you got 0.0402 Tesla. Okay, so I hope you understand the A. Fb equals to Fe when the charge is undeflected. Okay, B. If the electric field is suddenly switched off, calculate the radius of the electron circular path. Okay, so this is F equals to BQV. BQV. The F. Sorry, what I'm doing. Sorry, not F. So BQV equals to what? BQV equals to mv squared over r. The magnetic force equals to the centripetal force. Yes. So BQV, B you know now, 0.0402 Tesla. Charge, you know, charge of the electron given. Where's the charge of electron? Charge of the electron, you know, has 1.6 times 10⁻⁻19 to be used. Velocity, you know, the velocity 6.5 times 10⁶. Yeah, other information is, you know what? You're looking for the, calculate the radius, so you can find the R. You can book out the R. Speed, you know already. Speed, do you know? Yeah, speed given 6.5 times 10⁶. Mass is given 9.11 times 10⁻⁻31. So you should be able to get the answer. So important is the how to start with. B, the magnetic force equals to the centripetal force. So you find the radius. Any question from this slide? Okay. So this is BQ, what do you call magnetic field and electric field together. Okay. So this is the working one just now. Okay, class. So that's about what you call BQE, charge particle, charge particle experience force. Okay, now you're going to learn something totally new you never learned before. Something called Hall voltage. Okay, Hall voltage. Okay, class. I think before, I think we can go through this. Yeah. Okay. Hall voltage. Okay. Hall voltage. What is Hall voltage? Okay. So you need to understand a Hall voltage. If an electric current flows through a conductor in a magnetic field. Okay. Before we come to this story, let me explain to you in the whiteboard first about a Hall voltage. Okay. Okay. You see here, when you have what do you call electric field, you have a magnetic field. Okay, you have a plate. You have a plate. Okay, you have a plate like this conductor. Okay, conductor. So a current is passed through this conductor. The current is coming out here. You have a battery. You have to put a battery here. Okay. Okay. So now the current is flowing through this conductor. The current is flowing this way. Okay. But the electron moving this way, the opposite direction. Electrons moving this way, it's moving straight. The electron is like moving straight. Okay, now what we do, we apply a magnetic field upwards. We apply a magnetic field upwards. Apply a magnetic field upwards. Okay. So when you apply a magnetic field upwards, vertically up, what happened to the electron in this wire, in this conductor? The electron going to experience the magnetic force. Which direction the electron will experience the magnetic force? Okay, use your Fleming left-hand rule. Tell me which direction you're going to take. Is it yeah? Use your Fleming left-hand rule. FBI, B down. So it go to the side A or side B?
B.
A.
Side A, right? FBI.
Yeah,
B,
yeah.
B is into the downwards. Current is this way. Current is this way. Okay. So current is that way going up. So FBI. So the force is to the A, right?
Yeah.
The force is to the A. So force is to the A. Force is this direction. You get the force here. So what happened? The electron which is coming in, the electron have to go straight, but because of the magnetic force pulling it that way, the electrons start to drift to that direction. Okay. So all the electron which is coming out from this wire will drift to that direction. So electron will stuck here. All the electron will stuck here. They are not going to move straight to the wire. They're going to deflect it and stuck at the side here. Okay. So maybe the first 1 million electron, maybe. The first 1 million of electron coming out of the wire, because there is a magnetic field applied, all going to pull to the upwards to the A, all going to stuck on top. They drifted to the top. When this happens, this plate, the negative plate, the A plate is become negatively charged. They become negatively charged. Therefore, the B plate here will induce with positive charge. Okay, the opposite plate A is negatively charged because all electrons are accumulating there. So the opposite plate will be positively charged because a relative sign what the charges. Negative charge, positive charge is created. Okay, now if you have one plate negative charge, another plate positive charge, you create an electric field. Electric field was created. Okay, the electric field is which direction? Magnetic field is vertically down. Electric field provided is which direction? horizontally to this direction, the electric field. This is the electric field direction. Okay, horizontally, the electric field is actually B to A, right? Okay, so now electron not only affected by the B, electron also affected by electric field. Okay, now tell me what happened to the electron now. After 1 million electron drift to the other side, it create an electric field, a strong electric field. The electron which is comes out after 1 million, the following electron, the junior who coming out to this region, what will happen to that electron?
Straight line.
It goes straight line. Very good. The electron will go straight line. It will go straight line because of what? The magnetic force is acting towards A, but the electric force acting towards which direction? Towards B. The electric force is now going to act towards B. There is electric force now appear. So the balancing happens. Magnetic force acting towards A, electric force will act towards B. So the force will be balanced because the first 1 billion already sacrificed themselves to create the electric field, so that the electric field as strong as magnetic field to produce the same amount of force as the magnetic field, so that the following junior electron comes out can move in a straight line. So you get a current after that. So this effect is called Hall effect. It's called Hall effect. The drifting of electron to one side and production of a new electric field is called Hall effect. Okay, so now let's say someone go and join a voltmeter across this side A and B. This is the origin of what? This is the origin of A. This is your origin of B, right? The AB. Like imagine the A and the B like a parallel plate. The A and B like the parallel plate. This A, this B is like a parallel plate. You want to measure the voltage across it. Okay, this voltage is called Hall voltage. This is called Hall voltage. Hall voltage. Okay, Hall voltage. Okay, this Hall voltage is found to be proportional to the magnetic field strength. This is important. The Hall voltage generated to this edge is found to be proportional to the magnetic field strength. More stronger the magnetic field strength, not 1 million electron need to go to the side now. More stronger the B, now maybe 2 million electron have to drift to the side, so that they create a much more stronger electric field. So that the electric force and electric force due to electric and magnetic force equal, it goes straight. So you need a big voltage will be generated. Big magnetic field generate a big Hall voltage. So Hall voltage proportional to the magnetic field strength. So you need to understand this phenomenon. This is called Hall effect. Hall effect happens for a conductor. This only applies when there is a magnetic field applied. If you apply a magnetic field, the electron will drift, produces a Hall voltage. Okay, any question from here? Okay, this is the diagram. Okay, let me go back to the description in the slide for us to understand what is going on here. Okay, so let's try to understand the wording. So if an electric current flow through a conductor in a magnetic field, the magnetic field exerts a transverse force on the moving charge carrier, which tends to push them to one side. The electron will be pushed to one side. Okay. So the electron will be pushed to one side. Moving charge carriers, which tend to push them to one side. The part A, the side A of the conductor. This is most evident in the thin flat conductor. I tell you why is thin flat causes the very significant Hall voltage. We will get to know this later. Okay. So conductor is illustrated. A buildup of charge at the side of the conductor will balance this magnetic influence, producing a measurable voltage between the two sides of the conductor. The presence of this measurable transverse voltage is called Hall effect. It's called Hall effect. So yeah, so go to the next slide. Okay, this is another diagram. So you see the current is coming out. So imagine your electrons moving this way. Your electrons moving that way. Okay. Okay, different color maybe. Okay, so electron is moving that way. So now you see the magnetic field is directed upwards in this case, directed upwards. So magnetic field directed upwards. Current is coming this way. Which direction the magnetic force will happen? So B is upwards, FBI, B pointed upwards, okay, upwards. Current is coming this way, this direction, this way. So where's your magnetic force will be? Magnetic force will be the FM. FM will be this direction lah, to the side of, to the left side, So that's why the left side, all the electron will be deposited to the left side. That's why they put is negatively charged, all negatively charged. Because electron will drift to the left side, become negatively charged. So the opposite side become positively charged. So this create a Hall voltage. You see the VH is the voltmeter actually, voltmeter, but it's measuring Hall voltage now, we call it, measure Hall voltage. Okay. So this deposition of charge will create a electric field horizontally. Electricity which direction? Electric field happening this direction, right? To the left. The electric field is to the left. So create electric force to the right, because electron to the right. So the force balance, then create a Hall voltage. Final Hall voltage is formed. So the transverse voltage, Hall voltage measured in a Hall probe. Hall probe is a device measuring this Hall voltage as its origin of the magnetic force on the moving charge carrier. The magnetic force BQ, what do you call? This is BQV, BQV. BQV, E is actually Q, V is the drift velocity, we call it, they put D, D. Actually velocity, you can take it as velocity, and V, drift velocity of the charge, BQV. Okay, any question about this slide? Try to understand the Hall effect. Okay, so now we're going to prove. I told you what, the Hall voltage is directly proportional to B. Okay, how they got this, how they come to this conclusion? The Hall effects will be directly proportional to the B. Okay, that is the next slide derivation. Okay, these derivations you have to remember. Okay, these derivations you have to remember. Okay, let's go to prove how Hall voltage is directly proportional to B. Okay, that's the next slide. Okay, let's go through this. Okay, class, I think the background is a little not a poor contrast. Can you see the wordings, right?
Yeah, still can see.
Okay. Okay, what is the purpose we are doing this? We want to prove that. What we want to prove? VH proportional to the magnetic field strength. This is the final equation. The final equation we're going to form. VH is found to be proportional to the B. But how they got this, you have to know. In exam, they can ask this. Okay, first, I equals to NEAVD. Your AS knowledge. Current is, what is N here? Charge density, right? N is the charge density. How many charge contents per unit volume? E is what? The charge value, the elementary charge, the amount of charge possessed by one particle, charge of one particle. And what is A? A is the cross-sectional area of the conductor. Okay, I go back to the picture. Tell me which is your A. Which is your A here? Okay, let me clear this. Okay, which is your A here? Which region? On top side, let me mark here. Is it the A region? Or this is the B region? Or the C one? Which is your area? The cross-sectional area of the current, right, should be the C. Should be the C. This is the A. Okay, that means the A is actually the cross-sectional area of the current flows. Okay, so understand. So what is your A? Is the cross-sectional area of the slice of the conductor. Okay, now V is what? The drift velocity. The velocity that electron traveling. Okay. Now, second line, where N is the density, the charge, and A is WD. I hope I understand. A is WD, correct? A is WD, right? Go back to the equation, to the diagram. You see, A is actually what? The width times the thickness, D. D times the width is your cross-sectional area, correct? W times D is your A. So A is W times D. Okay. Okay, go back. So A is W times D. Okay, then, okay, now we're going to write magnetic force formula. What is magnetic force formula? Anyone? What is the magnetic force formula you learn? B QV, right? B QV. Okay. So how they got this formula? The magnetic force we know is BQV. Here the V is the drift velocity. So BQ, B and Q remain. Q we put as E, elementary charge. Drift velocity is what? Drift velocity we get it from the top here. Drift velocity is I over NEA, correct? I equals to NEA, yeah, correct. So yeah. So yeah. So EIB on top is, yeah, EIEB, what? EIB over NEA. So this is how you got this formula. Okay, what they did, the current has been the charge has been replaced in form of current. Okay, you get this formula. This is magnetic force. Okay, magnetic force due to magnet. Okay, so now when at equilibrium, when equilibrium achieved, magnetic force must be same as electric force. What? Electric force, the force due to electric force. Then what is the electric force formula? Anyone, what is the electric force formula you learned last time? How they got this? Electric force, what's the formula you know last time? Electric force is QE, right? Sorry, what is that? Yeah, QE, right? Q times E is your electric force, right? Okay, so QE is what? E, electric field strength, is what? V over D, right? V over D. Okay. What is V? V is the, the two plate, the voltage differences. In this case, the V is actually the Hall voltage. The Hall voltage is your V. Okay. Now what is D here? What is D here? D is the plate separation. Okay. Okay. What is the plate separation? Go back to the diagram. Okay. What is the plate separation here? Where's your electric field plate? What is the plate? Remember, electric field plate is which one? This one, the side one. This is your electric field plate. Now, your electric field plate is actually like this. I hope you can imagine. Okay, the side one. The side one. So this distance is the separation. So in this case, this D is actually what? Your W. W is your width. So be careful. Your electric field plate is at the side. At the side, the electric field has been formed is horizontally. Horizontally this way, from right to left lie, your electric field. Okay, so the D is actually W here. Okay, so we go back to the diagram, to the equation. So your F is QE, QV is all voltage, D is actually W. So that's why the formula become like this. The electric force is VH, voltage, charge is E, and the plate separation is W. Okay, so this is your magnetic force, this is your electric force. So to get the relation, the final relation, you link this equate with this. Hey class, 1 minute for you. Can you derive? There is one step missing here to get this final solution. Okay. Can you get this by equating these two? Can you get this final formula or not? 1 minute for you. Come on, give a try. Something need to be replaced. Okay, so let me do here. Erase this first. Okay. Okay, so FP, so EIB over NEA is equals to VHE over W. Okay. We are equating what? We are equating magnetic force equals to the electric force. So we're getting these two equations now. Okay, now how do you get this? So make VH as the subject. So VH you make as the subject. So bring the W and E the other side. Okay, I think here, yeah, bring the E here already is cancelled. So you bring the other side, become what? WIB over what at the bottom? And this E go down, right? NEA, correct? So this is what we got, correct? W go up, E goes down. So NEA at the bottom, WIB on top. But look at the equation. On top only IB. So W has been missing. At the bottom, we got NEA, but here NED. What replacement has been done? Okay, what is D? What is the D here means? Go back to the diagram. What is D? D is the thickness. This is your D, the thickness. W is here. The width is your W. Okay, D is the thickness. Okay. So what type of changes they have been done? The area has been replaced. The area they replaced with what? With IB NE. The area is actually what? Area is actually W times D. We put W times D here. So W cancelled. So then you get this formula. Okay. This could be a 3 marks question they can ask in exam. Derive proof that Hall voltage directly proportional to the magnetic field strength. You can ask in exam. Okay. So in this formula, be careful. The Hall voltage is equals to I. What is I? The current flow in the conductor. What is B? The magnetic field applied on the conductor. N is the charge density of the material. E is the charge of one part carrier. D is what? This is important. D is what? D is the thickness of the conductor. Okay, thickness of the conductor. Okay, now you tell me why they want the conductor to be very thick, very thin, must be very thin. Why they want the D to be very small? Why they want the D to be very small? Because the earlier description, they said one side of the conductor is most evident, the thin flat conductor. Why they say you must use a thin flat conductor to have a very what you call clear Hall voltage value from this equation? Because anyone can tell me? And the D is smaller, and the D is smaller, what happened? The Hall voltage is going to be larger. So you're going to have a significant Hall voltage value. So use a smaller slice as possible. If you use a thicker slice as possible, the Hall voltage is going to be very small. Originally, the Hall voltage is very, very small, very millivolt, maybe milli or microvolt. So you need to have a thin slice. A thin slice is going to create a very significant Hall voltage. So you need to use a thin slice. Okay. Okay. One pass here they asked the slice you use. Do you need to be a semiconductor or a metal to have a significant Hall voltage? What is your answer? Which can give you a significant Hall voltage value? A semiconductor slice plate, a slice, or a conductor, a metal conductor can give a significant Hall voltage value. Anyone? All in this equation. Semiconductor or a metal conductor can give a significant Hall voltage value. Anyone? All in this formula. That means this plate is a semiconductor. You take the Hall voltage reading. Then this plate replaced with the metal slice, and you take the Hall voltage value. which will have a more significant all voltage value, big all voltage value from this formula? Can you explain to me which one? I clear this, eh? Which one? Semiconductor or metal conductor? Which factor you need to look at? The semiconductor and metal conductor, what is different in terms of what? The N is different. The charge carrier is different. Semiconductor and metal conductor, which has a greater N? Metal or semiconductor? Which has a greater carrier?
Metal.
Metal has a greater carrier. So metal will have a greater N, and semiconductor has a smaller N. So which is going to give a big Hall voltage?
Semiconductor.
Semiconductor will give a big voltage because smaller charge carrier can give you a big Hall voltage. So in your Hall probe, right? Hall probe, a device which is going to measure the voltage, the Hall voltage. The type of slide they use inside is a semiconductor. They use a semiconductor. Why they use a semiconductor? Because N is small, you can have a significant Hall voltage. Okay, has been asked in past year. Why you use semiconductor? Because charge density is lower. Because all voltage and charge density inversely proportional. Therefore, we can get a significant Hall voltage value. Then they ask why the slice must be thinner. Because Hall voltage and thickness are inversely proportional. So thinner slice can give you a significant Hall voltage. That's the two questions they asked so far in exam. Okay, so yeah, this is today's lesson. Today you learned something a lot new, Hall voltage. You go to YouTube, you just type in Hall voltage, they show a very clear animation. Maybe the next class I can show you. Okay, you can understand better. Okay, class, any questions so far? Try to digest, try to understand this Hall voltage. The following class will be about this again. Okay, any question? So if you
no.
So I stop here. Okay, thank you, class.
Thank you, sir.
Thanks, sir.